Benoit has done an excellent job of introducing the subject and the general theoretical background. Before I begin, I should mention there are really two different types of implicit solvent model, and we've been talking about one of them. The type that we won't talk about are ones that are based solely on empirical data, and that's like the torsional statistical potential that Esmail discussed, where there's no modeling, you use the data as they come out of experimental information. The kind we're dealing with are ones where we have a physics-based potential functions for the solute, and we want to add to that a model for the solvent, get rid of the solvent, and model it somehow. So we have the idea of reduced representation. You might have an all-atom description for protein folding, and that takes too much time, even if you have $1 billion to spend on the problem. So you have to reduce and get rid of degrees of freedom. One is to remove the solvent, and you have the degrees of freedom of the solute, plus a model of the influence of the solvent. All the hydrophobic effects, you have to model them even though nobody really understands them, the screening, etc. And sometimes even this is too much. So Esmail dealt with a model which, instead of having all the degrees of freedom of the solute, he only had 2 degrees of freedom per amino acid, the 2 dihedral angles. So we have series of reduced representations. Benoit and I are talking about this kind of model where you have the solute degrees of freedom and you want to model the behavior of the solvent. And this is just one step in the process of multiscale modeling, where in our folding and refinement we have further reductions, and in the work on actin here they have even further reductions. Well, one of the popular models for modeling the continuum solvent is to separate the solvent contributions into the electrostatic and non-electrostatic. As Benoit discussed, most use the electrostatic model based on bourne theory, which can also be described as treating the solvent as a continuous distribution of point polarizable molecules. And if they're point polarizable molecules, you say, what about a liquid? A liquid is just not polarizability of the solvent. Solvent has dipoles which orient. But we'll get to that and discuss that later. The popular models have an SA in them, usually describing the non-electrostatic model with a simple surface tension, saying you have a repulsive interaction between the surface of the protein, for instance, and the surface. So the non-electrostatic model is a surface tension times an accessible surface area. This would imply the depletion of solvent near the surface. Well, at this point, I bring up my 3 golden rules of modeling, which I teach whenever I teach modeling. Rule number 1, when you're modeling a complex system, never believe your model. Instead, you follow rule 2, which is you test your model by taking it literally and seeing what the consequences are. And then there's rule number 3, which is don't forget rule number 1. So we want to test the model. Let's first test this surface tension model, which is in all of the GDSA type models. We test this by running calculations of the hydration layers about various proteins. These are cuts through the structure, and it shows the protein inside and outside is the solvent, represented as electron density of the solvent because we're using this for something else. And around, notice the scales are very different when you have depletion and enhancement of solvent density. There's a factor of 6 in the scale. Right around the protein surface, you have blue, which says exclusion. That's just the hardcore repulsion. That's the part of the pair distribution function where there's no overlap due to the Pauli repulsion. So that's an artifact. And you see just beyond that some red portions, which is an enhancement of density. And it was well known way back a long time ago, and Kirkwood introduced this into theories of solvation, that the hydration layer has an excess solvent density. That's completely the opposite from what is implied by the SA part of GBSA models. That doesn't stop anybody from using it. Then beyond this enhanced layer, you have a depletion layer and then a slight enhancement layer. So this is coming from all-atom MD simulations. We've frozen the protein to make this stuff much clearer. We also have, and I think it's present in our website, a theory HyPred, which enables reconstructing this density without MD simulations. So this is the MD simulation. This is the HyPred construction. This is the figure of merit of the fit. And you can see that the behavior is very similar. It's a little bit more smeared out in the theoretical reconstruction. And the theory is based on deriving from MD simulations in the first place a set of universal proximal radial distribution functions describing how the solvent electron density is built up dependent on the nature of the atom type, the amino acid, etc. This is still yet to be used to develop an implicit solvent model. The MD simulations take a few months to generate this data. This takes a couple of hours. So it's a huge simplification, but it's not something that you can use on the fly in MD implicit solvent simulations. So it's just one step in the process.
You really mean a couple of hours?
To get this? Oh, yeah, yeah.
It seems long to do that. I mean,
but we're calculating the non-uniform distribution dependent on the structure. So here you have enhancement near these residues. You don't have much enhancement near these. It's for the whole protein, not just one slice.
No, I understand.
And
that,
it's one
like,
CPU.
You know, if it was like basically, I guess there must be an ingredient I don't understand. Because if it was like a kind of a superposition of these G of R's.
Yeah, it is a superposition. It's just done with one CPU. If you did it parallel the way you did the MD simulation, it would be very quick.
Okay.
Yeah, so yes, it would be quick in that case. Okay, as Benoit said, the bourne model is based on the bourne theory for solvation. We have the water molecules oriented differently for the positive and negative ion. The bourne model calculates the self-energy of the charges, so it integrates outside the spheres around the charges, and it models the interaction between solute charges by a screening function. So the pair interaction of the charges is the product of the charges divided by R12, and it has a screening function, which is an empirically determined function, and we'll get to questions of that model. So implicit solvent models have several ingredients. One is you require that they be fast and accurate and have four properties. If we have dynamics, we need friction coefficients and random forces, as Benoit discussed. We need a dielectric screening of the charge-charge interactions. We need a solvation potential to model the hydrophobic effects and the non-electrostatic interactions. If you try typing this in Microsoft products, salvation gets changed to salvation, and maybe Bill Gates actually worked on this problem once before. A little bit of thought convinces you that the salvation potential and the friction coefficients should distinguish as much as possible between atomic type. So many of the models distinguish only between hydrophobic and hydrophilic, and you can't get very far with that. We've found that models which distinguish between aromatic and aliphatic carbons are necessary to get any reasonable result. So a little bit of chemical intuition goes quite a long way. What we did when we first approached this problem in the end of the 90s was to take every model that was simple, meaning quick, and test it. So we have 4 ingredients, and like a Chinese menu, we chose one from column A, one from column B. I think we invented a new field, combinatorial computational biophysics. Just tried all these possible models to see which ones agreed with explicit solvent simulations and have a chance of being reasonable. Benoit talked about all of the equations. I won't go through that anymore. We applied it first to some Medenkefwan dynamics, but then more interestingly, at the end of the 90s, there was this massive calculation of the partial folding of the villain headpiece with a 256 CPU Cray that was dedicated to this folding for 1 year. And we came along with our best implicit solvent model, an 800 megahertz single PC, which we ran for a couple of months to get a quarter of a microsecond trajectory. So we followed the same protocol as the Cray calculation. Start with the native state, heat it to 1,000 degrees for a nanosecond to denature it. So this is the unfolded state. It doesn't move far away, but it's completely denatured. And then we let it fold. And we look at how it behaves. The radius of gyration, or the RMSD, to the native structure. First, we see a collapse, then a burst phase, and then some subsequent burst phases. The time behavior is statistically identical to the Cray calculation, with one exception. When it collapses, the time necessary to squeeze out the last water is much faster. And Benoit also discussed that point intuitively, comes out of the calculation. But what's the interpretation of this? Very, very simple. If we look at the hydrophobic residues and explicitly show their atoms, the initial state is denatured. It's completely unphysical, not like anything that you would produce. And so the protein says, help, I'm exposed. And the first thing it does is have hydrophobic collapse. And in the hydrophobic collapse, in the rush to collapse, it trapped 2 polar residues in the hydrophobic environment. And they say, help, let me out of jail. And so the hydrophobic residues open up to let the hydrophilic groups out, and then they close up again. And that describes the burst phases. So we have a model which agrees qualitatively with the explicit solvent simulations. We've used that to analyze Sosnick's experiments on the nature of transition states for protein folding, and we're working on that with some other problems, which we'll get to. Another thing we've done in this business of not believing your models and testing them is we have to work with force fields. And many people are trained in a particular lab which uses a particular force field, and we come in as outsiders. So this was about 10 years ago. We had to decide which force fields to use for protein folding. And we chose to look at all of them and compare them. So we ran simulations for tripeptides and looked at the distribution of dihedral angles for the two central dihedral angles for the central residue. Those are like the torsional potentials or torsional distributions that Esmail showed. And we thought first we would generate them from simulations, but which force field to use. This is 7 different force fields which were available at the time. In my native language, Brooklynese, tell me what you want, and I'll tell you which force field to use to get it. This is wholly inadequate. This is for the unfolded state, and we realized that the force fields that were developed were devised for folded native state proteins, so there's no reason why they should be good for the unfolded state. And even in D.E. Shaw's simulations of protein folding, his native state has far too much helical content, and is not the native state, the unfolded state, and clearly our current force fields are inadequate for the unfolded state, and that's why Esmail used empirical statistical potentials for the unfolded state. Well, back to proteins and RNA. We did some work, as I mentioned, for developing a implicit solvent model for proteins, which does not work awfully. My characterization of implicit solvent models are they range from poor to completely physically absurd. So to say it's not working terribly is saying that it's about as good as we can do. But there are lots of implicit solvent models out there, and the general assumption in most of the community who haven't heard Benoit talk or read his review article is that an implicit solvent model is an implicit solvent model is an implicit solvent model, like Shakespeare. But they are very different for proteins. But one place where implicit solvent models have pretty much failed is for RNA. Failed because either they cost too much, almost as much as an explicit solvent simulation, or the RNA falls apart pretty quickly. So we've been working and working and working on devising an implicit solvent model for RNA. And here's an example of all-atom explicit solvent MD simulation. And this shows the initial conformation. Let me see if I can figure out how to do the movies. Yeah.
I'm sure you gave her the movie?
Yeah, I gave her the movie, but I don't know how to do it.
This next one, right?
No,
You're supposed to click just on the figure? You have the handle.
yeah. Okay, that's the all-atom explicit dynamics showing the fluctuation of the RNA. And that's what we'd like to describe. And this is for the RNA 430D. It's not just a hairpin or something trivial. It's a real system. And we'll go to the next case. NAMD put in a GB SA model. So
I
NAMD,
think they don't even have the SA. Do they have the SA?
do they have the SA in it?
The GBSA that they have? Yes. I thought they used only electrostatic part.
They recently added the sample.
Oh, the SASA's there too.
Yes.
Okay. So
Right.
NAMD is a great program. Let's see how they're. Oops. Tried clicking that. And this is opening up, bonds breaking. And this is only 20 nanoseconds. It's not very good.
What is happening?
A lot is happening, yeah.
It's like, you could say. Have much more to write about.
This is the same thing with our implicit solvent model. It has greening in it. It has a few parts which are not sticking together well, but it pretty much is staying together and is intact. I'm not sure whether the problem is the phosphate repulsions are too strong or the hydrogen bonding is not strong enough. And the problem is this is on an old program, which is one CPU, so it takes a long time to test things. And we're hoping to get it parallelized, but that's not trivial.
Do you have explicit ions?
In some of them, yes, we have put explicit ions. Let me see, I think this is tRNA, which is even more complicated. And SMAIL has explicit ions in there. And that is, aside from a few areas which are a little too flexible, is quite good and quite remarkable. So we're making progress with implicit solvent models for a really difficult system. Another thing we've worked on is the corrections to the bourne model. I mentioned that Bourne's model is equivalent to a continuous distribution of point polarizable molecules, and there's nothing in the model which says liquid. And there was a newfangled model, which is due to Dubai, 1925, with corrections by a couple of lightweights named Onsager and Kirkwood, which models the continuum as a uniform distribution of point polarizable dipoles. So dipoles looks like water. And we've investigated the difference between this model. I'll have to skip all the kind of algebra and what. This model and the bourne model. But what comes out of the Dubai model, if you have a single ion in solution, you have a distance-dependent dielectric permittivity, which has this sigmoidal shape, which is very similar to the model of screening that's used in the GB model. The physics is very much the same. And we've done a number of calculations with this Dubai model of quantities for which the bourne model fails badly. The bourne model, if you calculate the energy of transferring from a hydrophilic environment like water into a protein or into a lipid, the delta G for the bourne model is far too large. We calculated for the Dubai model and we cut it down by about a factor of 2, and this helps explain the problem with the bourne model, that it's just not including the fact that the dipoles are orienting, and this is modifying the field in a distance-dependent fashion. We also calculated quantities like the change in pKa on transfer, and also the screening function, but I'm just about running out of time, so I will skip that, and if anybody's interested, I can tell them some more. So things to remember: one, not all implicit solvent models are the same, and remember the golden rule, always. Questions? Yes.
So generally when you decide to choose the implicit solvent model, how big is your waters or how many waters are involved that you choose to use?
Well, there are no water molecules in any of the calculations. If you had a bound water that sits there for a long time, then you'd have to put it in. And Benoit has done a lot of that kind of calculation. It's also on the time scale question, which is relevant. If you're running dynamics and you're interested in nanosecond time scale, and the residence time is tens of picoseconds, you can ignore it. It's exchanging rapidly. Yes.
You mentioned the kind of four-week effect, so
In the model we use a SASA model for the non-electric, the interactions. It has the non-electrostatic plus the self-energy term all mixed in together. The SASA parameters have entropy in them. Yeah, it must have it. Yes? He's asking how temperature dependent are these things. We fit the SASA parameters to heats of formation or heats of solvation, and we had to use temperature dependence to get the temperature dependent parameters. But generally, we did the calculations only at 25 degrees Celsius. So we don't have enough data.
Can I add one thing? You know, in the classical treatment of the bourne model and of application of Poisson-Boltzmann, very often, like Barry Honig and Rasheen and Mike Gilson, like, you know, about 15, 20 years ago, were doing temperature derivative of Poisson-Boltzmann-like free energies. But typically what they assume is that only the dielectric constant depends on temperature. But in reality, all these models depend also on the radii, where you put the dielectric boundary. And, you know, when you treat the boundary as a fixed microscopic parameter, then it cannot have an intrinsic temperature dependence. And so you assume it doesn't depend on temperature, but in reality, it's an empirical parameter that depends on the thermodynamic state where you actually match your model. And so, you know, if you do temperature derivative of these models, you should assume that all the parameters actually are state dependent.
Yeah,
everything.
In our case, we had the SASA parameters as temperature dependent, but the radii should also be.
Everything.
And we need a lot of experimental data, stuff that I don't think any of the funding agencies would fund. Just basic data. More questions? Okay, thank you.